We've now reached the final part of our case study ex2 analysis. Part 3 of this case study focuses on the ParallelStreamFactorial class implementation, as well as analyzing the performance and accuracy of all 4 factorial implementations. In addition, Part 3 also summarizes the key points of the case study ex2 analysis. The source code we'll analyze here can be found in the ex2 project, in the FP folder, in my Modern Java GitHub repository. So we're now back in my IntelliJ project for case study ex2, where we'll take a look at the ParallelStreamFactorial class in the ImmutableState.java file. This class shows how the reduce operation in the Java Parallel Streams framework avoids sharing mutable state between threads in the Java common fork join pool. As you can see here, the factorial method is the entry point into this class. As always, it returns the factorial for the parameter n, using the Java Parallel Streams implementation this time, and the reduce terminal operation. Let's take a look at how this works. This is actually quite similar to the sequential stream implementation we looked at earlier. We start out by having a long stream from the values 1 to n, using the range closed factor method. We then go ahead and tell this stream to run as a parallel stream, which will run all the other operations concurrently in the context of the common fork join pool. We then convert the long value to a big integer using the map to obj intermediate operation. And then finally, we use the 3-parameter variant of the reduce method to perform pairwise reductions on elements in this stream to compute the factorial. And the nice thing about this approach is it completely avoids using shared mutable state whatsoever. Instead, we start out with using 1 as the initial value to reduce. We then use the multiply method on BigInteger as the accumulator, and then we go ahead and use the multiply method again as part of the combine phase. And when all is said and done, this will end up reducing the stream elements to compute the nth factorial without using any shared mutable state whatsoever. Now that we've walked through all 4 algorithm implementations, let's go ahead and run the test program. When the test program first begins to run, it starts by warming up the common fork join pool. Next, it computes the 1000th factorial using each of the 4 algorithms. For the sequential stream factorial, you can see it gives the same result as for the synchronized parallel factorial. And likewise, the parallel stream factorial also gives the same result. This result is quite large, and I won't show you all of it because it goes on and on forever here, because the 1000th factorial is very big. What I want you to notice, however, is that the buggy factorial gives a different result than the other 3 algorithms, indicating that it's not working properly. Let's now analyze the performance results, which are printed here from fastest to slowest. The fastest algorithm was the ParallelStreamFactorial implementation, which executed in around 1462 milliseconds. This is a little bit over twice as fast as the sequential stream factorial algorithm. The buggy factorial algorithm executed faster than the sequential stream factorial. However, the results were incorrect, so it doesn't matter how fast it performed because it gave the wrong results. And then finally, the synchronized parallel factorial algorithm executed much slower than the parallel stream factorial algorithm, and in fact was actually slower than the sequential stream algorithm, and that's because of all the excessive amounts of lock contention caused by the use of synchronized methods. Our analysis of case study ex2 during our code walkthrough underscores the following key points. First, the use of shared mutable state can cause chaos and insanity for concurrent and parallel programs. In particular, race conditions can arise due to unsynchronized access and updates to the mtotal field by multiple worker threads in the common fork join pool. Using shared mutable state can negatively affect both correctness and performance. For example, the buggy factorial algorithm gave the wrong result, even though it executed relatively efficiently. Likewise, eliminating the race conditions in the buggy factorial algorithm by adding synchronized methods addressed the correctness issue. However, it also incurred significant performance overhead due to the excessive lock contention. Modern Java support for immutable objects helps to address problems with using mutable shared state in concurrent and parallel programs. In particular, the ParallelStreamFactorial algorithm implementation yielded both a correct and an efficient solution. It gave the right result to compute the factorial for 1000, and it also executed much more efficiently than the other algorithm implementations. Also, converting a sequential modern Java program to a parallel modern Java program is often quite trivial. In particular, all we needed to do to convert the sequential stream factorial to the parallel stream factorial implementation was to add the parallel operation, which was a very minuscule change indeed. So that wraps up the third and final part of our analysis of case study ex2.